Hello everyone, my name is Paulus Velasco. I'm an application engineer at Intel, and today I will be talking about performance optimizations using VTune and Advisor. Getting good performance out of a modern HPC system requires us to take advantage of parallelism. And this parallelism is available at many different architectural layers of an HPC system. So for example, within a core, we have vectorization in terms of, we have parallelism in terms of vectorization, where a single vector instruction will do multiple operations in a single cycle. We have parallelism within a socket by having many cores on a single socket, and we have parallelism within a node by having multiple sockets on a single node. We also have parallelism on a cluster level, but this talk is not going to be focusing on that. The tools that we provide for performance metrics are basic compiler reports. We have VTune application performance snapshot that does kind of a coarse grain overview of performance of your application. We have Intel Advisor. That's a very good tool for ensuring proper vectorization and threading. We have Intel VTune, and that's the primary tool for getting performance counters and optimizing for things like cache, for example. And we also have Intel Trace Analyzer and Collector for profiling network issues. But since Theta is not based on Intel MPI, I will not be talking about Intel Trace Analyzer and Collector. All of the profiling tools that I'll be showing you today are available to download for free, and I highly suggest that you do that. Most of the time, we collect the results remotely and then copy them to our local system to use the GUI to explore the data. So in order to avoid X-forwarding, you're best off to go ahead and download the tools and install them on your local machine. And we support Linux, Windows, and Mac OS for viewing the data. Throughout this presentation, I'll primarily be using the Nbody code to highlight different features of VTune and Advisor. This Nbody gravity simulation was developed by Dr. Fabio Baruffal, and I forked it from his GitHub. And it's a great example that really helps us illustrate all the different steps in the performance optimization workflow. If we look at the simulation itself, we have a data structure that represents particles, and we have a double nested loop that goes over all of the particles and calculates accelerations. So since it's a double nested loop, there's no neighborless optimizations. It scales n squared. Before I get into dedicated performance analysis tools, I just want to mention compiler reports. And I say that they're free performance metrics in the sense that you don't need an additional tool, and you can just get the compiler to spit out performance optimization information. That can be quite handy. So if you just recompile your application with the QOPT report equals 5 flag enabled, a compiler report will be generated for each source file that you compile. And there's some very valuable information inside this report. So most importantly, I would say that there's vectorization information. So we'll tell you which loops were vectorized and what vector length was used. It will tell you a little bit about alignment, and if you're using scatter gather instructions. And in addition to that, you can also get more detailed information like registers, spills and fills, and any sort of software prefetching that might be happening. So the report itself is quite detailed and too much to go into, but I highly recommend that, if you haven't used a compiler report before, that you try this option and look at the report and see all the information that's available within it. Performance optimization is an iterative process. So normally you start with a code, you do some sort of a basis performance evaluation and profiling. Then according to the results that you got, you modify the code, verify that everything is correct, and profile again. So it's quite important to have this process automated and consistent. And in order to do that, we provide some helper scripts for you to get started with. So if you go into Soft Perf Tools, Intel, Advisor, or VTune, you'll see a qsub submission script, and there's quite a bit of things that happen within the script. So if you open one of these scripts, you'll see there's quite a few things happening there. So there's a job setup, so like the number of ranks, threads, hyperthreading, and affinity that you can tweak. The script itself takes binary as the first argument, and any of the subsequent arguments are going to be treated as arguments into your application itself. It sets up binary and source search directories, and I'll explain that in a second. It also saves all the results in a consistent manner, so it will be the timestamp with the binary name and the inputs as a result directory. So as you go through your tuning process, you're going to be able to keep a history of all these performance uh, profiles and be able to trace them back to a particular version of your code. And it also saves the cobalt files to the result directory. So you'll also be able to see how you ran the job and if there were any errors generated from your job. But I'd say the most important thing that it does is there's a setup that needs to be used on Theta in order to attach to a single, multiple, or all ranks. So normally it's the best idea is to profile a single rank, sometimes maybe even a single thread. And normally you could do this with, for example, Intel NPI run -G tool, but since Theta is a Cray system, we have to do a bit of a workaround that uses environment variables that Cobalt exports. So we use these environment variables to then attach to a single rank. The Nbody demonstration code has 8 or 9 different versions of the code, and each version is an optimization upon the previous version. So in this presentation, I'll mention, I think, primarily up to version 3. So version 0 is the initial implementation. In version 1, we add -x mic AVX512 flag to generate AVX512. Version 2 changes the code to only use floats as opposed to using floats and doubles. And finally, version 3 does an AOS to SOA transformation along with a SIMD reduce. The first dedicated performance tool that I will be talking about is Intel Advisor. And we have ALCF has a guide for how to use Advisor on Theta. So if you just follow this link, you can get some additional information. Intel Advisor is primarily a vectorization optimization tool. So it will tell you what loops or functions were vectorized and with what vector efficiency and vector instruction set. For loops or functions that are not vectorized, it will tell you the reason why the compiler was not able to auto vectorize that code. In addition to that, it also has some neat features for helping you vectorize code. So for example, sometimes code might not get vectorized because of compiler having to assume certain dependencies just to guarantee the correct result. So in that case, you could look at the code and determine if that dependency is real yourself, or you can use Advisor to tell that for you. Another big feature of Advisor is the Roofline model analysis. So Advisor will run your application. It will collect information about the G-flops, and then it will plot all the different kernels within your code on the roofline. And using the roofline model, you can then determine how much performance is still available for you in terms of the architecture you're running on. If you're not familiar with the roofline model, it is a performance model. So on the x-axis we have arithmetic intensity, which is a measure of how many computations we're doing in relation to how much memory we're pulling. And on the y-axis we have flops that are being achieved. So you'll see that we also have these horizontal lines, and these horizontal lines starting at the bottom we have scalar at peak, vector at peak, and FMA peak. So these are physical limits that you can get. For example, scalar at peak is the maximum performance that you can achieve if you don't use any vectorization at all. Then we have vector at peak is if you're using vectorization, and the final roofline is if you're using vectorization with FMAs. And then finally we have these slopes, and these slopes correspond to the bandwidth of different memory hierarchies that we have within a CPU. So we can have L1, L2, and DRAM bandwidth. So all of these numbers are measured at the beginning of a run. So these are not going to be looked up in some database. Advisor will actually run, for example, run stream in order to get actual bandwidth for your particular CPU. If you use the roofline model, your application or your kernel, your loop, or a function, it will appear as a dot somewhere on this plot. So if you appear under the scalar at peak, it's likely that you're not using vector instructions. So you need to vectorize in order to go up in bandwidth. If you land somewhere right above scalar at peak, it's likely that you are vectorizing, but you're not using the full SIMD length, for example. So you could have some issues with your vector efficiency. If you land somewhere near vector at peak, but still under the FMA, it could be an issue that we're not using FMA. So we can induce FMA usage and move up in the Y direction again. One important thing to understand about the roofline model is that it really tells us where we're at in terms of performance. It doesn't really tell us why we're there. So just because we're above the scalar at peak but under the vector at peak roofline, we said that it could be that we have a low vector efficiency, but other things can bring down that dot as well. So for example, if we have a lot of long latency operations like square roots, or if we have some memory issues or cache issues, all these different things can affect your performance and bring you down in the Y direction. If we land somewhere on the left side of the roofline model, we know that the arithmetic intensity to the left is quite low, so it's a lot more likely that we're experiencing some sort of a memory issue. So for example, if we land right near the DRAM bandwidth roofline, it is very likely that we have a case where we're not using any cache optimizations. So we need to make sure that we're using cache in a smart way in order to be limited by the bandwidth of L2 or L1 cache. And Finally, sometimes we're not able to really implement the optimizations that that we need in order to have cache reuse, for example, just because we're limited by the algorithm that we're trying to implement. So if that's the case, we really need to think about the algorithm that we're using and if there's any alternatives. In order to use Intel Advisor, it's recommended that you build your application with debug symbols. And other than that, the other primary requirement is that if you're running on Theta, you should be running out of projects rather than home, and that has to do with how Theta file systems are set up. There are 4 collections that Advisor can perform. So those would be survey, trip counts, dependencies, and memory access patterns. Advisor workflow starts with you collecting a survey. So survey does a lot of static analysis. It will look at what instruction set you're using and instruction mix and stuff like that. But it also will collect the call stack for your application. So it basically collects all the primary information that's needed for Advisor to function, and the subsequent analyses such as trip counts and dependencies, they require you to have collect survey already completed. Trip counts collection will run your application and count the trip counts on all of the loops that you have inside your application. It will also collect flop data. So if you want to generate a roofline, you have to run survey followed by trip counts with flop option enabled, and that will generate a result that will produce the roofline model for Advisor. So this two-step process, you can simplify that by just running collect roofline, and that is just a macro for running survey followed by trip counts and flops. Dependencies collection will run your application, and it will determine if compiler assumed dependencies and loops that the compiler was not able to vectorize automatically. It will confirm if those dependencies are real. And this collection in particular has quite a large overhead, as you'll notice, and I will show you some tips on how to manage these overheads so you can run a reasonable amount of time. Finally, memory access pattern analysis will look at the memory access patterns of your application, and for a particular data structure or a line of code, it will tell you the percentage of memory accesses that are unit stride, non-unit stride, or completely random. If you want to see what options are available for configuring each particular collection, Advisor has a very good help menu. So if you just do vectorization-h collect, it will show you all the different collections that are possible, but then you can string those commands together. So you could do -h collect survey, and it will give you options for the survey and so on. Another good way to get started with Advisor is you can configure analyses from the GUI, but normally where we're running the GUI and we're actually executing the Advisor collection tend to be different systems. But what you can do is you can go into the GUI and set up an analysis that you want to perform, and if you click that little terminal icon, it will show you the commands, the equivalent commands that you have to run on the command line interface. So you can just copy that into your JavaScript on Theta. So we want to run a roofline analysis on Theta. So we do module load Advisor that will put the latest version of Advisor into our environment, and then we go to projects, whatever your directory under projects is, and we make the application that we want to profile. We copy the script, and we can just qsub amplxe.qsub, and then the application with whatever parameters it needs. Once the job completes, we want to view the result. X forwarding is not really recommended on Theta. Most of the time, it's just going to be is just going to be too slow. So for that reason, it's best to have a local version of Advisor on your laptop, and then we can either tar uh, the Advisor result along with the binary and the sources, because we want to be able to look at the sources from our local machine, or we can use an Advisor snapshot option. So this will generate an Advisor file. If you do pack, it will also use some compression to reduce the size of the output, and then we specify a cache sources and cache binaries option as well to include the sources and the binaries in this file. And after that, we can just SCP the file to our local machine and open it up on the GUI. Once we open the report, we get dropped down to the summary window, and here you'll see some basic information about the collection. So for example, total elapsed time and percentage of overall runtime that was spent in vectorized loops versus scalar code. It will also show you which instruction sets were used, and if you collected flops, we'll show you flops as well. We can switch over to Survey and Roofline tab, and this would be the primary tab for Advisor. So right off the bat, we see a warning toolbar at the top. It just says that we have a higher instruction set available. If you compile version 0 uh, on some other machine other than Theta, it will compile with SSE2 instead of AVX512. So that was the case for this result, and we can see that it's telling us that since we're running on the KNL, we have AVX512 available, so we should recompile with those options. In the function call sites and loops, we can see we have one primary compute loop, and we'll see some potential performance issues that Advisor might flag. We'll see the self time and total time. The difference between these two is self time would be the time taken, the time spent inside this loop in particular, whereas total time shows the time uh, spent in this loop along with any children that this loop might call. So if, for example, if we see that self time and total time are equal, we know that this is a kind of a leaf node. At the bottom, we'll see the source tab, and that's why it was important to copy our sources whenever we were copying the results to our local machine, so that we can see this. We can see Advisor information line by line for whatever source files that we have. So again, line by line, we'll see total time and loop function time, and Advisor will also put some diagnostic information in this view as well. So it will tell us that this loop was vectorized, which data types were used, and if there's any potential performance issues. If we follow advice from the previous tab and recompile the application with AVX512 enabled, we'll see two things. That first, the elapsed time dropped down significantly from the previous collection, and we'll see the change in the vector ISA that was used for our compute loop. We'll see the vector length increased, and we'll also see that efficiency decreased. So in the previous tab it was 91, and in this tab it's 51, and that is just because of a longer vector length is harder to achieve optimal efficiency. One, if we look at the bottom, there's also code analytics tab here as well. And one interesting metric here is the AVX512 mask usage. So generally, this mask has a direct effect on the vectorization efficiency that you achieve. If you have no branching, no conditionals, and every single SIMD lane of your AVX512 register is being executed, this mask usage would be at 100%. So looking at this mask usage and our vectorization efficiency, we can speculate that the low efficiency is not due to any sort of mask instruction use, but most likely due to scatter gather operations. And if we look at possible performance issues, uh, the performance issues changed from the previous collection, and now we have possible ineffective memory access pattern as being a potential issue that's flagged. Also on this window, we'll see that we have a small roofline, and we'll see an instruction mix between memory, compute, and other instructions. There is another way to access the roofline plot, and that is this button on the left. And if we click that, we're switched to the cache-aware roofline model view. So for analyzing our result, since this is a single-threaded application, no MPI, no OpenMP, we select the use single-threaded roofs option. Or if you're using a different version of Advisor, you might have the option to select the number of threads to use. So we would just select one, and we can also use this window here to change the filtering and how our kernel is displayed. So you can change the percentage cutoffs for what's shown up as a big red dot, a yellow dot, or a green dot, and that would be dependent on the percentage of overall runtime that that particular function is taking. So looking at this roofline model, we see that we are right around the scalar at peak, but we know that we're using vector instructions, so it's not vectorization or vectorization efficiency that's most likely the problem. And given the previous suggestion that there's possible inefficient memory access present in our compute loop, the next step is clear for us. We can run memory access pattern analysis. In order to run the memory access pattern analysis, we can go back to our application and modify the amplxe.qsub script to collect survey followed by map analysis, and that will do both steps. Or we can modify the script to skip the survey collection and use an advisor directory that's already present from the previous run whenever we needed to collect survey for trip counts and flops. So we run this analysis, and we can go into the next tab over at the top to the right of the survey and roofline, and we get into the refinement reports window. And here we'll see our compute loop and the memory access patterns for it. So we see that we have an even split between unit stride, uniform non-unit, and non-uniform accesses. Looking at this result, we see that we have constant stride and gather stride access for the same line of code. And if we look at the data structure that we're using, we'll see why that is. The reason why we're getting gather operations in our compute loop is because we're using an AOS data structure. So that would be array of structures. So the base structure itself that we have is we have a structure called particle that has 3 arrays with 3 elements each, representing position, velocity, and acceleration. We also have a scalar mass. But the way, whenever we create an array of particles, it's a very natural way for someone to implement something like this. Whenever we implement particle this way, we'll see that the way this is laid out in memory is that our positions, for example, are going to be contiguous in memory, but the positions for the next particle over are going to be strided. So every time we have to iterate through all the particles, we get a portion that we can load sequentially, but we have to do a gather access every time we need to get to the next particle. So we get the strided access required in order to fill a vector register. What we can do is we can change our data structure from AOS to SOA. So instead of having an array of particles, we just have a single particles data structure uh, where all of the positions in the x direction and velocities are going to be stored contiguously in memory. So it's going to change the way our application looks and how we operate on this particle data. But if we implement it this way, we can now load a vector register in a single load. As far as memory access patterns, we have unit stride, where all the elements are sequential in memory, and we can load many of these values in a single load instruction. Then the next one would be constant stride, where we iterate by a constant increment, and this is not as optimal as far as access goes, but it's still not too bad because KNL has prefetching, so it might help you out by loading the subsequent elements before you actually need them. And finally, we have irregular or non-unit stride access, where we have just random access in memory, and this has the highest penalty in terms of performance. So we figured out the performance issue, and that was the presence of a data structure that's not optimal. We went ahead and implemented the change. We went from AOS to SOA, recompiled the application, ran the roofline analysis again, and we see that the performance is actually lower. If we go into the survey, you'll immediately notice that our compute loop is no longer vectorized. And among the performance issues, it says, the loop was scalar, it's not vectorized because of vector dependence. So normally, we could go in, look at the source code, and try to figure out if there actually is a dependency or not. We can force vectorization and then check results. Or alternatively, we can run dependency analysis and have advisor verify whether this dependency is real or not. In order to run the dependency analysis, again, we modify the amplxe.qsub script to collect survey followed by dependencies. We run the analysis. We open the result and see that advisor does indeed confirm a read after write dependency. One nice thing about advisor is that it actually gives you some very actionable recommendations. So if we go to the tab to the right where it says recommendations, it says resolve dependency, and actually gives us a couple of ways that we can try doing that. So we're going to use a second option that's shown, and that is to use SIMD reductions. We go back into our code, we add pragma omp SIMD with the reduction on the variable that's needed, recompile the application, rerun the roofline analysis, and we now look at the roofline, and we see drastically improved performance, and you can see that our roofline is now much higher. So the question is where do we go from here? How much performance is still available? And we kind of need to stop and evaluate and think what our next steps in our optimization workflow are going to be. Now I'd like to explore some of the limitations of the roofline model. If you go into the advisor roofline and you hover over a particular kernel, it will show you some additional information for that kernel. So it will show performance in G-flops, L1 arithmetic intensity, the time, and the bandwidth achieved. And it will also show you how far away from the roofline you are. Looking at this roofline, we see that we have a 4.3x speedup still missing, and that would be the speedup going all the way to the roof of single precision FMA. But remember that in order to be able to achieve this performance, that roofline is for essentially computing just pure FMAs. And in real codes, that is not normally the case. So in order to do an FMA, you need to have an equal mix of multiplies and adds. On the left here, you'll see the compute kernel that we're analyzing. So we can go in and kind of explore the source, and we can count the total number of possible FMA operations that we're doing in the single loop. So of all the adds and multiplies that we're doing here, there's only 3 out of 29 operations that can be converted to FMAs. So that is really just a 10% FMA ratio, and we can scale our roofline to uh, to give us the match performance for this FMA ratio. So that would just be the single precision vector add scaled by 1.1. So we see that our real roofline that we can achieve for this particular algorithm without making any algorithmic changes is actually closer to 44 G-flops. And if we divide our current performance by that, we'll see that we're actually achieving 40% of peak. Okay, so that's much better than 20-ish% that we had before, prior to adjusting the achievable roofline. But where does the 60% go, right? Is it vectorization efficiency? Is it long latency operations such as the square root, or is it something maybe like poor cache utilization? So if we look at the advisor result, we know for a fact that vectorization efficiency is not an issue. Actually, it's at 97%, so it's pretty much as good as it gets. So maybe it's it's that complex operation. Maybe that inverse square root is very, very expensive. So I did a test to kind of illustrate the effect of introducing that inverse square root into their code. So on the left, I have the original code, and on the right, I replaced the inverse square root with just a simple multiply to kind of illustrate the impact on performance that it has. So if we do that, we actually get 31 G-flops, and now we're much closer to 70% of the roofline. So that's pretty good. So maybe the last 30% is actually just due to poor cache utilization, and this is where advisor stops. Cache performance can be profiled using performance counters, and for collecting information regarding performance counters, we have a tool called VTune. So VTune is very good at getting metrics from inside your core. And if you want to get some additional information, user guides on how to use VTune on Theta, you can follow the ALCF user guide at the link below. VTune is a system profiler, meaning you can profile an entire system. So that could be even a multi-socket system. So it's accurate and it has low overheads. You can collect performance metrics using perf or using Intel subdriver, and that is the recommended driver for using VTune. It can tell you a whole bunch of information about what's happening within your CPU, so it can give you core and on-core metrics. In addition to collecting performance metrics, VTune is very good about displaying the data and grouping the data in a certain way. It also gives you a call stack. So one of the nicest things about VTune is really the interface and using the interface to figure out the performance issues that you might have. VTune, you'll see that VTune has a lot of different collections or analyses that you can perform, and you can think of these as analyses as a collection of knobs that get turned on or off. So, for example, um, most systems do not provide you access to all the performance counters at the same time. You can only access a certain amount. So if you wanted to get a full profile of your application using all the performance metrics, getting all the performance metrics that are available on the system in terms of performance counters, we have a microarchitecture exploration view. So that will run your application and it will do time multiplexing, switching between reprogramming performance counters in order to give you the full spectrum of available information. The only issue with that being that you might have to run your application for a longer amount of time to get good number of samples, good coverage on your performance counters. We have HPC performance view, and uh, that is that is a view that's more suitable for analyzing potential issues with threading. We have memory access, I/O, concurrency. We also have GPU support, and you'll see these three collections that are in a lighter blue. For those, we have Python support, and I will be talking about Python uh, at a second half of this presentation. In order to run, for example, a microarchitecture exploration analysis, we again have to be in projects. So we go to projects, whatever application directory you have. We do module load vtune, and then we need to edit the makefile to make it link dynamically. So this is not necessary, but for example, if you're using OpenMP and you would like additional OpenMP information to be collected, VTune comes with instrumented OpenMP runtimes, so it needs dynamic linking in order to switch out the OpenMP runtime for its own in order to give you more detailed metrics. Same way as Advisor, you can configure and even run your analyses if you're running on a local target using the VTune GUI. But for me personally, whenever I just started using VTune, the GUI was a very good way to explore all the different options that are available to you without pouring through documentation. So you can configure whatever analysis you want to be run on the GUI, and then at the bottom right you'll see the command line button, and that will give you the equivalent that needs to be run on your remote HPC system. So we can start off with something simple. For example, let's say we introduced OpenMP into our application, and we're just interested if we're actually using all the cores that are available on the system. So we can do a hotspot analysis. So we submit the amplxe.qsub that was modified to collect analyses. You might want to add enable OpenMP flag there, and collect the results. We tar it up, copy it to our local machine, and open up on the GUI, and we're dropped into the summary window. So right off the bat, you'll see the CPU time, how long the application ran on our machine, and you'll see that spin time is flagged as red, and it's very high. Red is bad. So if we look at the CPU usage histogram at the bottom, it essentially shows us how much of the runtime, uh, the percentage of runtime that used a certain number of threads. And looking at this example, we'll see that most of the time we're using 0 threads or just one thread. And you can see that falls under poor. One thing to note is that this is a KNO with 4-way hyperthreading, so it plotted all of the threads on this histogram. So if you're not using hyperthreading, for example, you can actually change these sliders um, to be representative of that. we can switch over to the bottom up view, and this is the primary view for VTune. So at the top half, there's essentially our call stack with time utilization, and you'll see spin time there. And at the bottom half, we have all of our different threads or processes that are being analyzed. So you'll see that first off, you'll see that we have lib iomp5.so. So that means that this particular example was either the hotspots were ran without the analyze OpenMP flag enabled, or the application was not compiled with dash dynamic, because if those two things were done, this OpenMP SO would not be seen here, and the spin time would actually be correctly attributed to the OpenMP region that's inducing the spin time. But looking at the timeline here, we see that we do have a lot of threads. Threads are spawned, but they're essentially, most of the time is spent waiting, and that's just because we don't really have enough work to keep all these threads busy. Now I will go over a couple of different examples, different codes, and different collections that can be done with VTune to show you some of the ways to use the GUI. So if you right click on the CPU time, normally by default it's shown in seconds, but I think for me it would be more useful to have this time shown as a percentage of total. So if you right click on that, you can change the time to %. Next up, we have this grouping tab. The default grouping is function and then call stack. But we can change that to group by source function then call stack, and this is a good case for that. So for example, we see two functions called AA, and we can see that they're from the same source file. So why would they be shown up separately, right? The reason for that is if you click this triangle, and if you click the triangle, it will first show you where AA was called from, and you can keep clicking these triangles all the way down until you get uh, all the way to the top of main, right? So that's why it's bottom up view. You start from the bottom, and you can explore all the way to the top. So the reason why these functions show up two times is because the path they take to get to main is actually differ. So this function is called from a few different places in the code. So, but if we change the grouping to source, you'll see that these two get grouped into a single one. So now we see that this function is actually um, a much higher percentage of the overall runtime. Another thing to note here is at the bottom we see show inline functions. So we could disable this, right? We can switch to hide inline functions, and you'll see that our top time consumer AA, right, it disappeared, and now we just have the single function spinner U that is taking up nearly a third of the overall execution time. And that was just because AA was actually called from spinner U, but it was inlined into spinner U. So one reason why we would want to know something like that is we just found out that the compiler chose to inline AA into the spinner U routine. So potentially we could do that ourselves by hand, and then we have this spinner U routine as a larger optimization target, so we can look into some potential code changes within this larger function in order to get some sort of a performance benefit. Next up, we can switch between displaying functions only, loops only, or loops and functions. So right now you see only functions being displayed, but we might want to switch to loops because loops oftentimes are optimization targets, so whether that's improvements for vectorization or something like that. Certain collections allow you to also enable the collection of stack information, and so normally VTune does not do this, and uh, I think only software collections, driverless collections can collect stack information. But if you collect the stack information, then you can switch over to the top-down tree view. So one thing to note is, if you did not enable stacks, or you basically just don't see the top-down tree tab, just know that that information is not available for this particular collection, or the information was not collected. So we can switch over to the top-down tree, and it is essentially an inverse of the bottom-up. So whereas in the previous view, this loop was at the top, now it became a leaf node of this tree, right? Starting from main, we can go down until we get to this particular loop. And I like this view because it gives you a good coarse grain overview of where you're spending your time as you go as you drill down from main into the actual application. If you look here, you'll notice that this is actually a drop-down menu, and this is the view that's being used to display the data. So whenever I said that all the different collections that are available on VTune, they're just essentially sets of knobs that are turned on or off. So the information that those knobs collect makes certain views either available or not available. So some collections collect a whole lot more information than others. For example, Microarchitecture exploration will probably collect the most information, and all the information that it collects is going to be a lot more than is required for hotspots. So for this hotspots view, we see that we have a threading efficiency and HPC performance characterization views, right? So we could switch over to HPC performance characterization and get data displayed in a different way, but keep in mind that the HPC performance characterization view information that's available within it might be limited, just because hotspots does not collect as much information as HPC performance characterization view collection would have. Okay, so this is a microarchitecture exploration view, and uh, this is by far the collection that I use the most with VTune, and I just wanted to note a few things in this collection. You'll notice that some of these data fields are grayed out, and that is because this is one of those collections that collects all the performance counters, or at least a lot of them, and it has to do time multiplexing in order to uh, cover all the different counters that it collects. So if you don't run your application for a long enough time, it's not going to get enough samples, and it's going to mark the metric as unreliable. And whenever it does that, it will appear as grayed out. You'll also notice that uh, some of these uh, some of these rows cells get colored red, and that's indicating a certain performance issue, something that you might want to take a look at and investigate. And if you hover over them, it will explain the metric and the formula on how it calculates whether to highlight something as red or not. Another thing is, you'll notice for this collection that there's this period of time that the collection was paused. So you can start your collection paused and resume collecting after a certain amount of time. Uh, that's something that you can do from the command line. So you can use the help menu to see how to do that, or look at the VTune documentation page. But if you want, you can also instrument your code. There's a library called ITT Notify, and if you insert those calls into your library, it will trigger the start and stop of the collection from within your application. So if you're interested in collecting just a very specific region of your code, and you need good coverage on that section alone, you can instrument your code and do it that way. In addition to viewing the GUI, oftentimes, we want to collect performance metrics over time or for many different binaries. So we want to set up some sort of an automated workflow where we get all this information. So you can generate text file or CSV reports using VTune. If you want to get more information on that, again, you can use the help menu. So we can do help report, and then we'll see all the different reports that we can do. So for example, let's do report hotspots. Once we do that, we can do report hotspots, give it the directory of the result, and if we add this dash column equals question mark option, it will look at the result, finalize it, and it will dump out all of the metrics that were collected during this run. If we do the report again, but we can be pretty specific, so we can say display only loops and limit the top 5% consumers, and for those consumers only show me the L2 cache it and like the percentage of time. It will spit it out, and there's another option to dump it to a file in a CSV format. The help menu is pretty good at getting you started on using the text file reports. If you really want to export the GUI, you have to do this unset LD preload on Theta and then run the GUI. But again, the best way to view this data is to download it to your local machine and use the local GUI with the import result. So let's go back to the example we were working with and answer this question where we were left off. Is it poor cache utilization? So we can go in and run microarchitecture exploration analysis for the binary that we had. This is the view that you're gonna get. So you have the number of instructions retired. You have your CPI rate. So we'll see that our CPI is really good. We see nothing is front end bound, and that makes sense. We have a very simple kernel. We see there's no bad speculation, and that's because we don't have any branching. We see that the metrics for back-end bound and retiring are pretty high. So essentially what this is saying is that close to 60% of our instructions are retiring successfully without being stalled, and the rest are being stalled in the backend. We can expand the backend column, and this is where we're going to find our L1, L2 hit rates and stuff like that. So one thing to note here is that depending on which platform you run VTune on, different CPUs have different performance counters available. So this view might change from system to system. Again, if you dump the text report, this is essentially what that looks like. Okay, so let's quickly just go back to our application, look at the source code, set some expectations, and then use VTune to verify. We know we have 32K L1 and 1 megabyte L2 cache for KNL. On the innermost loop, we are accessing 4 different points in memory using the J counter, so we can count that out to be 2K elements, that we can cache in the L1 for the inner loop. And if we go and look at the entire double nested loop, we see that we access 3 additional data structures here. These points, we're hoping they're already going to be cached in memory because they're being accessed here. If we look at this, we can expect going past 2K elements, we're going to start losing caching in L1, and going past 35, 36K elements, we're going to start losing our cache performance in L2. I went into the application and I ran the application with all these different parameters. And since the application reports G-flops, we can kind of see that is exactly what we're seeing. We see a local peak at 2K, and then once we get to 35K, we see a rapid decrease in performance. I then went in and made a script that essentially did the same thing, except it attached VTune to every one of those runs, and it dumped the CSV reports for this collection. So we can essentially see our hypothesis confirmed. Going past 2K elements, we see a decrease in our L1 hit ratio, and once we get past 35K, we start seeing decreases in our L2. The L2 hit bound ratio as 0 here. Well, that makes sense because we fit into L1. We don't need to go into L2. But you'll notice that our L2 hit bound stays 100% passless. And this metric shows the percentage of overall cycles that were impacted by latencies caused by an L2 hit. If you remember the KNL architecture, the mesh layout, just because you have an L2 hit, there can still be a penalty to get that piece of information from one end of the chip to another. This would just signify that we are spending time in the mesh. And then finally we have L2 misbound that is essentially 0 until we get to 35K, and then we start seeing penalties for that. So I just wanted to quickly mention profiling Python applications with VTune. In the previous slides, I showed you 3 of the analyses that were highlighted in different colors for which we have Python support, and that essentially means that we can run Python and we can preserve the Python call stack and once we display the result. So in order to do a Python profiling run, you just specify Python as the executable that you want to profile, and then whatever arguments go after that. So you can run that. We could get a result that looks pretty similar to what we had before. Regular C code. So you'll see that we have some functions here that are in the Python call stack. So what we can do now is we can go into the bottom-up view, and you'll see that we're able to display our native Python code, and on the right here you'll see the time taken for each particular line of code inside the Python layer. So we can identify regions that are taking a long time inside our Python application, and maybe replace those with a more performant library, or maybe write something in C and call it from Python. Another tool that I wanted to quickly mention was the application performance snapshot, and that also works with Python. So it's a very coarse grain level tool that will profile your application. You can run this at scale with many ranks, many threads, and it will give you a report in HTML format that you can then just display in your browser. So in order to do this on Theta, just modulo VTune and export my node port. So this is one of the variables that's set up in the example scripts that I provided for VTune and Advisor. And after that, just run your application as you would normally, with just prepending APS before the executable. And once it's done, you can run this report, and we get a view like this. So you'll see that overall our application is MPI bound. We'll see which MPI calls we're using, along with some OpenMP and memory footprint information as well. If you get the slides for this presentation, the last few slides are essentially some common issues and tips and tricks for example, speeding up finalization. So I suggest that you look at those at your own time. But this concludes my presentation on VTune and Advisor.